All right, you've got a homework assignment due on Friday, and then the next one after that will be on Wednesday of next week, and then the following thing that's due is the project on the 17th of April. Now I'm still working through grading the initial submissions for the network maps, and I should be able to go even more quickly through the reservoir sizing. But what you can already be doing is calculating the cost of the network. And remember that when it comes to the pipe network, there's only certain pipe sizes that you can select from. And those are the commercially available pipe sizes that are defined in the handout. And it also says what the price per meter is for each of those sizes. And so the overall cost of the network is going to be the number of meters of each pipe that you've got multiplied by the price per meter for that size. And you add it up for all of the pipes in your network. And then for the reservoir, you need to interpolate the price from the given data. So I've given you a couple of sizes, I think maybe like 2,000 cubic meters and 5,000 cubic meters, but it doesn't mean that you're going to build only those sizes. So it's a little bit different from the pipes where you're limited to the commercially available pipes. For the reservoir, you can assume that you can build exactly the size that you need, which is the maximum volume accumulated multiplied by 1.25. But you get the price data by extrapolating or interpolating depending on whether you're outside the range of that highest value, in which case you just assume that the trend continues linearly, or if it's between the 2 points, then you just interpolate. So that's what you can be working on right now, is you already have the updated demand estimations, so you could be explaining what you changed there. Some of the mistakes that you made earlier you need to address in the full write-up, kind of closing the loop on what your adjustment in design assumptions was. Yeah?
For the final report, do we need to change our network, like pipe sizes, to fit the commercial available?
If you haven't already, then absolutely yes. Yeah. So like if, for example, when you were doing your initial design for the pipe network, if you said 440 millimeters, then you can't keep that for your final submission. It needs to be limited only to the commercially available sizes that are mentioned in the handout. Are there other questions? Yeah.
So with our first submission that we did, any changes? Do you want us to keep the old one and then do like a change log?
No, it doesn't have to be anything quite that dramatic. You know, like I can go back to the first submission and look at it. So if you just describe in like maybe bullet points what are the changes that you made, or you can do it in paragraph form, but it doesn't have to be like track changes, or, I mean, I'm not looking for any particular format for how you express that. You can just choose whatever you think feels natural. Any other questions about the announcements? We're going to continue talking a little bit about hydraulic jumps today, specifically about how we can estimate the length of the hydraulic jump, and then we're going to look at underflow gates. So this is where we left off after Monday's class. We did an example in Monday's class, and we calculated what would be the downstream depth, and in particular we were looking at this figure at the end of class on Monday. And this is the momentum depth diagram, and what it showed is that when you have a relatively, when the upstream Froude number is close to 1, that means that you've got barely supercritical flow upstream. It's not going to jump much. If your upstream depth is pretty close to the critical depth, remember that the point that's the furthest to the left on the momentum depth diagram, this is the critical depth. And so if upstream it's already pretty close to the critical depth, then downstream it's not going to be much of a change. But the further away you get from the critical depth upstream, so below this critical point are the upstream supercritical depths. The higher the momentum function is upstream, then you're going to have a much larger downstream differential. So the length of this line represents the change in the water depth through the hydraulic jump. So what these series of images illustrates is the different flow patterns that exist beneath the surface for different types of hydraulic jumps. And they classify hydraulic jumps on the basis of their upstream Froude number. And so, for example, an undular jump is one that has a Froude number of between 1 and 1.7 upstream. So it's just barely supercritical, and so therefore it goes through a pretty non-dramatic transition where you could maybe only barely notice the change in depth from upstream to downstream. And the water surface is slightly ruffled, but there aren't really dramatic standing rollers and lots of entrained air. If you look at the flow patterns under the surface, there is some interaction with the bottom of the channel, and that's considered a negative thing. We do apply value judgments to some extent to these hydraulic jumps because of the risk of scour and damage to the channel that can occur if there is a consistent pattern of flow going down. And so undular jump is considered not particularly desirable, but it's also not particularly damaging because there just simply isn't that much energy in the water if it's barely supercritical. Now, a weak jump has more energy because the upstream Froude number is higher, but if you look at the flow patterns, they don't typically go down towards the bottom of the channel. So we don't generally get that worked up about a weak jump either. Now, the ratio of the upstream and downstream depths is getting a little bit more distinctive, where you probably could notice it visually. And the rollers, the rolling surface variations are beginning to be more noticeable and distinct. An oscillating jump is maybe the first time where we get a little bit uneasy. These are considered destructive, and we generally try and avoid having oscillating jump because you'll notice that the flow patterns are going down towards the channel, and now there's enough energy in the water that if the channel isn't somehow armored, or if it's not like a strong surface like concrete or asphalt or some other engineered surface, then it's likely that it's going to scour over time. It can cause erosion to the banks of the channel because there are a lot of waves that set up that in addition to the rollers, there are waves downstream that get propagated. Now, kind of the sweet spot is a stable jump where the Froude number is between 4.5 and 9 upstream prior to the hydraulic jump. And why a stable jump is considered desirable is it's not having patterns of jets or velocity that heads downward towards the bottom of the channel, and also the waves don't propagate downstream after the hydraulic jump has stabilized downstream. So it's considered the most advantageous and well-balanced way of dissipating energy when there's a hydraulic jump. And so, like, how do you control something like this is largely about what's downstream of the jump, because we can put in a weir or a gate or something else to control the water level downstream, and then that would force the hydraulic jump to occur at maybe a sooner depth than it would otherwise, where it could have set up as an oscillating jump instead. So if you look, the ratio of upstream to downstream depth in a stable jump is between 5.9 and 12. So that's a really dramatic increase in depth downstream. And so stable jump is kind of the sweet spot. And if we get beyond that, a strong jump is once again kind of risky, just simply because there's so much energy that's being dissipated. The Froude number upstream is greater than 9. So it's kind of a really dramatic situation where you have to have carefully constructed and designed stilling basins to make sure that the waves settle out and that there isn't a stream bank erosion after the jump. Now, moving to these different methods that exist to predict how long the hydraulic jump is. You'll remember that the formulas we've looked at so far have only been to calculate the ratio of the depths. So this formula tells you, like, what's the upstream depth and what's the downstream depth. So Y1 versus Y2, but it doesn't tell you how long the hydraulic jump is and what sort of a distance, for example, you would maybe have to put in concrete to try and protect the channel from scour and erosion and all the energy dissipation that's going on. So the first figure that our book offers is a nomograph that was generated by the Bureau of Reclamation. And if you're not familiar with the Bureau of Reclamation, they fill a lot of the same roles that the Army Corps of Engineers does here in the East. The Bureau of Reclamation, I don't know, maybe just for historical reasons, is more dominant in the western part of the United States, but they manage dams and some waterways. There are some of the roles that don't overlap, but they have a lot of hydraulic analysis duties, and so some of the things that you may already associate with the Army Corps of Engineers is also done by the Bureau of Reclamation. But this nomograph, what it is this thick black line is a curve with which what we do is start with the upstream Froude number, and so it still has these hydraulic jump labels that we've just gone through. You start with the upstream Froude number and you would intersect the point of that curve and go to the left, and then what it tells you is the ratio of the jump length to the downstream depth. So to use it, what you'd do is you'd first know the upstream depth. From that, you could calculate the upstream Froude number. You'd use the hydraulic jump equation that we've seen before. It's called the Bellinger momentum equation. We'd calculate the downstream depth, y2, from the momentum equation. And then from the nomograph, we'd find the ratio of the jump length to the depth. And then that would tell us the jump length, which is, you can see, defined as from when the rollers begin to where the water depth is stabilized and now it's flowing at whatever steady uniform depth that's downstream. So they differentiate between the length of the jump and the length of the rollers. And so here L sub R is the part of the hydraulic jump where you can see like lots of foamy water. It looks maybe white, and there's the air that's entrained because it's the most dramatic part of the hydraulic jump. But then the water level is still increasing gradually for some additional distance beyond the roller distance. So this Bureau of Reclamation nomograph tells you the overall length of the hydraulic jump. Another part of the book suggests that, like, if you know the overall length of the hydraulic jump, that the rollers usually vary from about 40% of the overall jump length to about 70% of the overall jump length. And it varies based on the Froude number. You know, when you've got a relatively low Froude number, saying down in the range of 3, then it would be about 40% of the jump length. But then when you have a high upstream Froude number, then it would represent about 70% of the jump length. So using this nomograph is one approach to predicting how long the hydraulic jump would be. Another is called the Hager equation, which you can see it's just on the basis of observation and curve fitting. They took lots of different measurements in a variety of circumstances and predict the jump length on the basis of the Froude number and the upstream depth prior to the hydraulic jump. And then our book even mentions what they call just another jump equation. They don't even bother naming it, but just suggesting that the length of the hydraulic jump has some coefficient that varies from between 5 and 6.9, and you multiply that by the elevation difference between upstream and downstream, and then that would give you the jump length. So just to get some practice with these, and also to apply the Bellinger momentum equation again, let's consider the case of water flowing through a channel that is 25 centimeters wide, and it's going at a velocity of 5 meters per second. And we know the depth upstream is 10 centimeters. So we've got a channel. We don't know, for example, the end value. We don't know the slope of the channel. We don't necessarily need that. It's just we're told that there's a hydraulic jump. So there's some hydraulic jump. Let me draw this with a little bit more care. So we've got the rollers. The jump gradually increases, and then it's flowing at its normal depth again. Y1, the upstream depth, we're told, is 10 centimeters. So 0.10 meters. we'd like to know what's the downstream depth in this case, and then after we know the downstream depth and the other stuff like the Froude number and so on, then we're going to calculate the length of the jump. So the first part of this, find the depth after the hydraulic jump, is find y2. So we've got the equation for the Froude number here, and we know that the water is flowing at a velocity of 5 meters per second before the jump. And then remember that the channel is 25 centimeters wide. So you'll need that for the top width and for the cross-sectional area. We're assuming that this is a rectangular channel that's carrying the flow. So let me pause for a second and give you a moment to calculate the downstream depth after the jump and also the Froude number, which we'll then use together. We'll go through all of the jump length calculations together. So they gave us the velocity, the depth, and the width of the channel. So from all those three things, we can calculate the flow rate. This flow rate is velocity times area. And with the flow rate and the Froude number equation, we get the Froude number 5.05. So we can predict the downstream depth. And now the next part of this is we want to know how long is the hydraulic jump. Not just what is the elevation differential, but the distance from where the hydraulic jump starts to where the water elevation stops changing. So L sub j is this distance. How long is that? Well, according to this nomograph, if we start with a Froude number of 5.05, what we do is we're here in the middle between 4 and 6. We go up, find the point of intersection. It looks like it's just slightly higher than 6. You know, we have to be a little bit careful here in reading the intercept, but I'd say that that's probably close to 6.1. So what that says is that the L sub j divided by y2 is 6.1. Now we know y2, we just calculated that. So L sub j is 6.1 times the depth we just calculated of 0.667 meters. So that tells us that the hydraulic jump length, according to the Bureau of Reclamation, 4.06 meters would be the anticipated length of this hydraulic jump. So from the figure, we got this ratio of the jump length to the downstream depth, and multiplying that by the downstream depth, 4.06 meters. Now we've got two other equations just to, you know, examine the situation from a couple of different viewpoints. The Hager equation says that the ratio of the jump length to the upstream depth is 220 times tan h of the Froude number upstream divided by 22. I don't know how many of your calculators have tan h function, but what I get is that the jump length according to this method would be 4.96 meters. And then the book has this other formula that it calls another hydraulic jump equation, where it suggested the coefficient A is between, what'd they say, 5 and 6.9. So if we just pick some value in the approximate middle of that, you know, if we just use the A factor of 5.5, and then the difference in the elevations, so the downstream depth minus the upstream depth, that would give us the lowest of the hydraulic jump lengths, 3.1. So which one is right? Maybe we'd have to actually measure it in the field to know, but we have at the minimum about 3 meters, at the maximum about 5 meters. And so that would help us, like if we wanted to be on the safe side, to know how long the hydraulic jump is going to extend beyond the point at which it begins. All right, so that's all we'll talk about for hydraulic jumps, except for the fact that there's oftentimes hydraulic jumps that emerge downstream of underflow gates. And that's the next thing that we're talking about, is underflow gates. So an underflow gate could be just as simple as a piece of metal that's in a frame, which the metal plate is lifted, sometimes even just by hand. So a gate like this could be used in an irrigation situation where a farmer has a series of canals that irrigate water onto fields. And gates can be far more sophisticated and have a lot more mass to them. But they follow the same principles, and that is that there is pressure pushing on the gate and forcing it closed up against the frame. And so there's going to be a certain amount of force that you have to lift up on the frame just by virtue of the mass and the accompanying weight of the plate, but then also the pressure of the water pressing against the gate as well. There can be a lot of these gates that feed into flow equalization basins in water treatment plants, where when you've got sanitary sewage coming into a treatment plant, the biological systems that are used to break down pollutants in sanitary sewage, they operate at a pretty constant rate, where bacteria can't be turned on and turned up really dynamically in the same way that you can turn up a mechanical pump. You can't turn up bacteria. So we have to feed the bacteria that break down biological waste in wastewater treatment plants at a more constant rate. And so flow equalization basins will take the incoming sewage during peak times and store it briefly, and then meter it into the plant overnight when the flow rate into the plant would be otherwise kind of low. So it's maybe the reverse of the storage tanks that you designed for your network, where you had a constant flow in but a variable flow out. Flow equalization basins at wastewater treatment plants have variable flows coming in, but they let out a constant flow rate. So there will be a lot of gates in situations like that where you may have storm water coming in from one direction and sanitary sewage coming in from other, and then you have to have different gates to open and close the flows out of the flow equalization basin. There are radial gates like this that have a curved surface, which are used to regulate the flow through canals. And the advantage of a radial flow gate like this compared to these heavy frames that we were looking at earlier is that when there's water pressing on this frame, it increases the friction and makes it more difficult to lift it up if there's water pressure pushing the gate closed. But if you have a radial gate like this, since the hydrostatic forces are pushing through a central axis, there isn't the same friction effect. So you'd only need to lift up the weight of the gate rather than also the additional friction forces that are caused by the gate getting smashed closed. What we want to know about is the relationship between water depth and flow rate. In other words, how deep will the water get upstream of a gate for a certain flow rate? Because these gates can act as chokes. Like if you have water flowing through a channel and you put a gate to try and regulate how much water is going through, then the water upstream is going to pool until it comes into some equilibrium. And so that's what we need to look at the energy equation to understand, is what's the relationship between the depths and the flow rates that exist through the channel. And so you can see that this is a specific energy analysis, just like we've done in other open channel situations where the flow was unsteady or non-uniform. In this case, this could be steady, but it's non-uniform because the depths are changing in the direction of flow. So here, the variable definitions, Y1 is just talking about the depth of water before the gate. You can see Y sub G is how high the opening is in the gate. and the water continues to contract because the water is accelerating due to the pressure that exists behind the gate. If we go down through the fluid, the pressure is increasing, and so the water is pushing the fluid underneath the gate, and it continues to accelerate briefly, and so it contracts downward until it reaches some point of minimum depth, and that's the Y2 that we're talking about in the second part of this energy equation. And the relationship between the gate, the depth of the water just as it exits the gate, Y sub G, and then the ultimate depth that it contracts to, is there's some C sub C, which is the coefficient of contraction. That's the ratio of those two depths. And I'll show you a formula in just a moment on how we can calculate or estimate the coefficient of contraction. But before we look at that, it typically varies from 0.59 to 0.62, but we have equations that we can use to estimate it. If we have a rectangular channel, then we can calculate the flow per unit width for a gate. And this is useful because it's pretty common to have a rectangular channel where the water comes towards a gate. That was the case here in this situation. You see you've got a vertical sidewall, and the gate just goes downward the entire width of the channel. So if we want to know the flow per unit width, we can estimate that by looking at the upstream and the downstream depths. And so this equation could estimate, assuming no energy loss. Now, that's not a very good assumption. We'll see in a moment how we correct for that. But if we just strictly applied this energy equation between the upstream and downstream of the gate, then we could calculate the flow per unit width according to this approach. But we'll look at how we account for what's called the discharge coefficient, C sub D, which takes into account the coefficient of contraction and the energy losses that occur. So whether it is a vertical gate or a radial gate, the same formulas apply, and there's some upstream depth, Y1, there is some gate height, and some texts call it Y sub G, some, I think the FE manual calls it W. It's just, the height that the water is at as it flows under the gate, and then it contracts a little bit more and comes to some ultimate minimum depth, Y2. And you'll notice that here, this is showing the total energy line, which also is sometimes called the energy grade line, is constant through the gate, and that the added energy is turned into velocity head, because prior to the gate, you've got lots of depth but a relatively low velocity. The water's moving slowly towards the gate, but it accelerates and moves at a very high velocity under the gate. So this is supercritical flow in a lot of cases. And if we have a mild slope, then flow under the gate is one of the main ways that a hydraulic jump can form downstream, because you've got supercritical flow where it shouldn't necessarily exist, which is to say on a mild slope. So we apply the orifice equation to find out the flow rate coming out from under the gate. And so there's the discharge coefficient, which takes into account energy losses and the contraction that occurs. B is the width of the channel, and we would typically apply this to a rectangular channel. W is how high the gate is opened. In some of the previous slides and other texts, they'll refer to that depth as Y sub G, the depth of water right at the gate. And then the square root of 2G, and then the depth of the water. In hydraulics, in fluid mechanics, we sometimes call that H. The velocity is the square root of 2GH, where it's just the distance from the center line of the opening up to the water surface in the case of the orifice equation in fluid mechanics. But here, just for simplicity, rather than measuring from the center line of the opening, we measure from all the way to the bottom of the channel and upward, and then we could factor in any variation into the discharge coefficient. So the orifice equation is how we find out how high of a water depth upstream predicts a certain flow rate. And so let's get some practice with this. We've got a canal that's 4.3 meters wide, and it's a rectangular canal. And the gate is across the entire width of that. The upstream depth, Y1, is 2.7 meters. And, oh no, the gate is 1.5 meters wide. So it's not the entire width of the channel. If we were going to look at this in the top view, the channel is wider than the opening of the gate. So let me show you from the top. If we've got water flowing through the channel like this, then the channel width is 4.3 meters in this top view. And the water is flowing along, but then the gate is actually only at a width of 1.5 meters. So here's 1.5 meters is the gate. So you could think of it as like that there's like a concrete wall, and then the gate is being raised and lowered in some opening in the concrete wall. So from the side view, Y1 is 2.7 meters, and the gate opening is 45 centimeters. So W is 45 centimeters. And then after contracting, so meaning here at Y2, the depth is 27.5. So what we need to know, the flow rate that's going through the gate, is first of all you should calculate the coefficient of contraction. So find C sub C. And the definition of C sub C you can get right here from the diagram. So C sub C is Y2 divided by W. Next, then you'll calculate the discharge coefficient. So then find C sub D, and then finally find Q. So the coefficient of contraction is just the ratio of the final contracted depth to the gate height. So 0.6111 for this case. We use the coefficient of contraction to calculate the discharge coefficient. So the discharge coefficient is basically a correction factor that says how far this deviates from if there was no energy loss. Now there is energy loss because there is contact with the ground surface, so that would be like a frictional kind of a loss. There is the energy that's lost as the water is approaching, and the flow patterns are reestablishing as they approach that gate. So here the 0.5822 just says that the flow rate is going to be about 42% less than we'd expect if there was no energy loss. Like if this was an inviscid fluid that has no viscosity, then the flow rate would be higher. But it's not, so we need to account for the energy losses that occur. So what we'd expect is that if the channel width is the channel width is 4.3, but the water is only going through a gate that's 1.5 meters wide, then 2.86 cubic meters per second is going to be the flow rate through the gate there. So think about what are some of the unknowns that you could face in a problem like this. If I gave you the flow rate, I could ask you to find out like what is the upstream depth. that would be required to achieve a certain flow rate. And that would be tricky because y1, the upstream depth, would not only be here under the square root of 2g y1, but there's also a y1 term that comes into play in the discharge coefficient. Sometimes the problem could ask how wide should the gate be to limit the water rise to a certain height and to convey a certain flow rate. So you could also be needing to solve for b, the width of the gate. So those are just a couple of ideas related to gates. And we'll look at a problem that has both the gate example and also a hydraulic jump forming downstream after the gate. So it's all interrelated since you've got supercritical flow after a gate. We're out of time for today, so this homework 11 is due on Friday. I'll see you then.